Welcome to the inflating balloon. A spherical balloon is inflating with helium at a rate of 100 pi feet cubed per minute. So that would be dV dt, because although it's missing the little cube, that would be dV dt. Our balloon, of course, is spherical because in calculus land we don't have those funny looking oblong ellipse balloons. No, we have the spherical ones. How fast is the balloon's radius increasing? So that would be dr dt. So we know dV dt, we want dr dt. At the instant the balloon's radius is 5 feet, and then on the next page we'll find ds dt. All right, so the equation for volume of a sphere is 4/3 pi r cubed. Right, so we're going to take the derivative, right, to solve for the rate of increase in the radius. So dV dt equals, and then 4/3 pi is just a coefficient. So that's going to be 4/3 pi, and then using the power rule, the 3 would come in front, and then r squared. And then, of course, that would be dr dt. Let's simplify that. So that would be dV dt equals, the 3's will cancel. So now that's going to be 4 pi r squared dr dt. We want to solve for dr dt, so let's divide both sides by 4 pi r squared. So we have dV dt divided by, that's a d, by 4 pi r squared is equal to dr dt. Having problems with my d's here. All right, so now we've got to do is plug it in, right? Plug in dV dt, plug in r, and simplify. So dV dt was 100 pi divided by 4 pi, and then the radius is 5. So that's 100 pi divided by 100 pi. So dr dt is going to be 1, this is terms of feet, so 1 foot is dr dt. That's the rate of change in the radius when the volume is increasing at a rate of 100 pi feet cubed. The radius is increasing at 1 foot. Oh, we need it per minute. Sorry, per minute. Almost forgot the unit of time. So 1 foot, dr dt is 1 foot per minute. Remember that, we'll need that to find ds dt. And of course I have it written down right there below too. The balloon's radius is increasing at a rate of 1 foot per minute. At the instant, the balloon's radius is 5 feet. If I had to give the answer, I'd probably also add the entire thing here, not just the solving. All right, so you're taking the AP test and it asks you for dr dt, right? Because dr dt is not 1 foot per minute all of the time, right? It's 1 foot per minute the instant the balloon's radius is 5 feet. So if you're taking the AP test, and don't forget to include the entire answer. Okay. All right, so now we're going to find, so a spherical balloon, same problem. How fast is the surface area increasing? Formula for surface area is 4 pi r squared. Isn't it interesting? It's the happens to be the derivative of volume of a sphere. Right, and it's same thing, same time span when it's when the radius is 5 feet. So we take the derivative. ds dt is equal to, right? So 4 pi is a coefficient. The 2 moves in front, and then we have r. So let's simplify that. ds dt, oh, excuse me, dr dt. Don't forget dr dt. ds dt equals 8 pi dr dt. Oh, excuse me, 8 pi r dr dt. And we have all the values we need, right? We don't need the dV dt, but we have r, it's going to be 5. We know what dr dt is, right? That's 1 foot per minute. And that's it. We're solving for ds dt. So ds dt equals 8 times pi times 5 times 1, or, so, yeah, I can squeeze it in here, and then I have the answer below. ds dt equals 40 pi, this would be feet squared per minute. And that's all there is to it. All right, so the balloon's surface area is increasing at a rate of 40 pi feet squared per minute. At the instant, the balloon's radius is 5 feet. All right, so another problem done. Join me in the next podcast. Bye for now.